This question it's not really posed as a question. We're trying to analyze what data we should be looking at for a confidence interval or a test. Now, the question is, we would be testing, and we're talking about a difference of means, is whether there was improvement between different groups. And so that means that those are the actual average values we should be dealing with would be the treatment group versus the control group. What that means is this is sample 1, this is sample 2, and this is just combined. And we're not going to use combined data to calculate values. We're going to split the data. And the different values we're talking about, we have the pre-test and the post-test, but I care about the improvement score. And I'm going to be comparing the improvement score between group 1 and group 2. Mu1 minus mu2 for the population, and our samples would be 26 minus 16.67. This is X bar 1 and X bar 2. Those are the values we would be using. Example 6 on page 183. We want to know which statement is the most accurate. Here we have students tested a claim that the mean improvement in math scores was greater than the mean improvement for the treatment was greater than that for the control, and the p-value is 0.16. They also calculated a 90% confidence interval. Now, in our confidence interval, we got negative 6.9 to 25.6. Just like I previously said, talking about 0 is in this interval, so there is not a difference between the improvement scores of the two different groups. And our p-value is not small, so we're not rejecting. We're basically not saying that there's a difference here. We're just going to go ahead and not reject this statement. We're not going to accept it, we're just not going to reject it. The students made a mistake. The interval should not have negative numbers. That's not true. The interval contains 0 because the difference in gains between the treatment and controls was not statistically significant. That's true. The p-value tells us it's not statistically significant, and the interval of 0 agrees with that statement. And again, the students did not make a mistake. Another example for checkpoints, and we're calculating the 95% confidence interval. How do we do this? We want to calculate an interval. We're going to go to StatCrunch to calculate these values in the next video. We have different sample sizes here. We have our sample sizes, we have our means, and we have our standard deviations. So just like before, when we would enter in X bar and S and do a 1-sample t-test, we're going to do a 2-sample t-test or a 2-sample confidence interval. Using these calculations, if you want to know the confidence interval formula, you would have X bar 1 minus X bar 2 plus or minus the t critical value times the standard error, which is S1 squared over N1 plus S2 squared over N2. We could run all that by hand, or we could use StatCrunch, and this is our winner for StatCrunch. Checkpoint 8, we're asked about an appropriate conclusion. We have our sample sizes here. We have the standard error of the results, the degrees of freedom, our test statistic, and our p-value. Our p-value is 0.005. That is low, meaning we reject the null, we do have evidence. Low means reject, have evidence. The sample provides significant evidence that students at University 1 drink more than students at University 2. We have to look at what our null and our alternative hypothesis is. When you have your null and your alternative, we would be rejecting this and we would be saying there's evidence for this. They want to know whether students at University 1 drink more than students at University 2. So we would do the average here equal to 0, their difference, and then we would say 1 minus 2 is greater than 0. We can ignore this part right here about not being statistically significant because our p-value is small. Now this part right here says we can't use a t-test because the variables are likely skewed to the right. Well, our sample sizes are large. 40 and 49 are both greater than or equal to 30, so this statement is invalid then, which means we're good to go and we do have evidence. Finally, question 9, we have a high school student named David. He did a study about music abilities. We talked about this problem when we were doing experimental design in the very beginning of this semester. We know they played Anthrax music, they played Mozart music, and wanted to know if the rats ran faster. And we did have evidence back in the day before we knew how to run significance tests. What conclusions can we draw? Well, the difference are statistically significant at the 1% level. That means we have evidence. So the rats did run faster, but we need to talk about the fact that each group had 23 or 24 rats in it. Now, that means that our sample sizes aren't 30, okay? So we need to know whether the population is normal or not. The Anthrax groups were slower, the Mozart group was faster. The differences are not heavily skewed in any group. That's our key indicator. Since N is less than 30 and is not greater than or equal to 30, then we're looking at whether there are outliers or skewness. And because it's not heavily skewed, we're okay to use this data. And since our sample size is small, we're good. We can ignore the sample size being too small because of the statement about being not heavily skewed. He has proven that heavy metal music causes rats to run slower. That's a lofty statement there with the causing. The causation, remember, if we're doing observations versus experiments, we get into some issues. And then even with experiments, causation is kind of tricky. So let's hold off on that for just a minute. There is evidence that heavy metal music causes rats to run slower and classical music causes run. Okay, so evidence again. And then we can't draw any conclusion. Well, there's not any flaws in the experimental design. We said that from back in module 4. So right now, he's proven versus evidence. We can't say that he has proven for sure. We can say that there's evidence for the claim here. So there's evidence that heavy metal music causes rats to run slower while classical causes them to run faster. So this is the better statement because remember, it's all about the wording. Now we're going to hop over to StatCrunch and show the calculations that we did in this module.